Hello, good evening. Welcome to the second week of the interactive live session for the course Geomorphic Processes, Landforms and Landscape. And the instructor is Professor Javedan Malik from IIT Kanpur, Department of Earth Sciences, and myself, Ananya. So, we have already done 1 week of this interactive live session. So, in the first week, we mostly dealt with the basics of what this course is going to address. Okay, so you have a 8-week course. So every week we are going to learn something. Firstly we will learn the basics, some concepts that are required for better understanding of geomorphic processes. So in the last week, we had talked about what are geomorphic processes, what are actually you know different agents that actually work, and the role they play in changing the landscape of the earth. And we also learned a bit in like the basics of what is the interior of the earth, and what are the different kind of geomorphic processes that are there. And we also started learning a little bit about how the environment in itself, the changes that we see across the globe. Okay, so most of it, how it is actually natural. Okay, they are all naturally occurring, and the changes that we see in the atmosphere or in the hydrological cycle, geological cycle, in the biological sphere. Okay, all of these interact with each other, and how the changes in them at a natural scale is to be expected. But when the intensity of it increases, and when the human influence actually causes a rise or increase in the intensity of these changes, that is when the geomorphic processes, they actually turn into hazards, okay, natural hazards. So these are some of the few basic conceptual things that we had talked about in the previous week. We had stopped at Earth's energy budget. So in the previous uh, week, we had learnt about the how much solar energy is received by the earth, okay, and how they are bifurcated into or how they are used up, or reflected back, due to different processes or due to different materials that are encompassing the earth. So this is kind of an exercise which will help you understand that the balance, okay, the balance between the energy that is absorbed or that is received by the earth is actually equal. It has to be equal to the energy that is lost from the surface of the earth. Okay, so there has to be a balance, as it's a universal law also, that um, you cannot create or you cannot destroy energy. So the same concept actually even applies when it comes to the solar radiation that is received from the received by the earth, and the energy that is given out by the earth. So the
And
yes.
a question, ma'am. Last week we have discussed about the albedo of Earth.
Yes.
Man, albedo of Venus is about 70%.
Okay.
Ma'am, what are the effects of albedo on Venus or other planets or Jovian planets?
Okay, the effect of albedo. So, when you are saying albedo is 70%, so 70% of what? Like, is that a value, or are you comparing it with the albedo of something else?
Mm, I think I'm not sure. This is a approximate value. I think that albedo is something, ma'am, which are the energy which planets or just Earth जो है,
Hmm.
मतलब, as Earth it absorbs about 30%.
Okay.
But Venus have 70% albedo. That is why it have hottest planet.
Okay, so see, albedo is the the phenomenon where the energy or the light that is received is actually reflected back. So possibly, if you're saying that, I think the Venus, since Venus is closest to the sun. Okay, so I am not sure whether the 70% is the albedo effect or the 70% is what it is absorbing. So I am not sure about the albedo of Venus per se. So it is a bit difficult for me to answer this right now. Maybe I can look into it and maybe post a answer on the discussion forum. Is that
Ma'am,
okay?
yes, ma'am, about 70%. Brightest object in the sky after sun and moon is Venus.
Okay.
And albedo is about 70%. मैम मेरे पास एक डेटा था,
हाँ हाँ.
तो मैंने कहीं से स्टडी किया था, तो वहां पे था, इस दैट इज वाई हार्टेस्ट प्लेनेट है।
ओके.
और एल्बिडो ऑफ अर्थ लगभग 30% है।
अच्छा. तो इट कैन हैपन कि वीनस का जो कॉम्पोजिशन है वो शायद एक रोल प्ले करता हो। जैसे मतलब ऑन अर्थ द एल्बिडो इफेक्ट इज लोअर compared to Venus is also because the water will absorb, the vegetation absorbs the light. Okay, so it's only the snow cover that is actually giving that albedo effect. है ना, the
यस,
thing that we had studied. So
यस, यस मैम।
maybe the higher kind of just 1 minute. Yeah. So the higher albedo effect of the Venus could be due to the composition, which is actually reflecting most of the light that is being received. And since the most amount of solar radiation will be received by Venus because it's closer to Sun compared to Earth. So I think these two could be, possible reasons why we have a higher albedo for Venus than Earth.
यस
But
मैम।
yeah, so but to give you a proper answer, I will have to look into it once. So I will most probably try to post an answer about this on the discussion forum latest by tomorrow. So hopefully that will clarify.
यस मैम।
Okay.
यस मैम।
Okay. I'll just note it down. A bit of Venus. Cool. Okay, so I'll look into the albedo effect for the Venus planet, and I'll post the clarification of what actually kind of controls the albedo effect for different planets in the solar system. Okay, so back to the radiation balance for Earth's surface. Okay, so we had learned that the for the Earth's surface. Okay, so the solar radiation that is coming through. Okay, so if we are considering 100 units of total solar radiation that is coming through the atmosphere. Okay, and it's incident on the Earth. Now, out of these 100 units, 51 units are actually absorbed, okay, by the Earth's surface. Okay, so over here you can see the processes that are causing an energy gain, okay, at Earth's surface. Okay, so we are first of all trying to understand what are the processes and how much processes that are causing the energy gain at the Earth's surface, and the amount of the solar radiation units, okay, that are being that are helping in the gain of this energy. So the first process is absorption of solar radiation. Okay, so we have 51 units of those, and absorption of infrared radiation from atmosphere. Okay, so if you remember, we had talked about uh, we are actually talking about this part. Okay, so 1 units of solar radiation is absorbed by the Earth's surface, which is giving the which is giving the energy gain. Okay, So in that sense, we are talking in that respect. Now the Earth's radiation, okay, the energy 51 units are incident on the Earth. It is absorbed of it has absorbed the solar radiation. Now from those 51 units, okay, so then later on 96 units, okay, so the percentage wise, okay, so the 96 units are absorbed, okay, 96 units of infrared radiation is also absorbed from the atmosphere. So this is also giving rise to the energy gain of the Earth's surface. Okay, if we go back to the this part. So we are talking about the infrared radiation, that is the infrared radiation that is given out, okay, from the atmosphere, the one which is I think I'll just have to revise this once again to get the flow myself also. Okay, so we'll just revise this quickly. So we have 342 watts of solar radiation, okay, solar energy falling on 1 square meter of Earth's surface. Okay, so we are only considering 1 square meter, and we will try to understand what is the energy balance, okay, between the energy gain and energy loss by different aspects of the Earth. So we will consider atmosphere, we will consider Earth's surface, okay, and then together Earth as a whole system we are going to understand. So if 100 units are falling in 1 square meter area, okay, 30 of it is scattered back or reflected back to space. So we are considering 30 units which are not actually even reaching the Earth's surface, okay, or sorry, not reaching as in it is not absorbed, okay. So 30% that is not absorbed by the Earth's surface, okay, and it is reflected back. So we have 6 units that are scattered by the air, water vapor and aerosols in atmosphere, okay. 20 units are reflected back by the clouds and 4 reflected back by the Earth's surface, okay. So this is already 30 is gone. Now remaining 70 units of the solar radiation, okay, it will make its way uh, to the Earth's atmosphere, into the atmosphere, okay, into the, so it will pass through the atmosphere, the 70, okay. So from that you have 19 units are absorbed by the atmosphere and the clouds again, and the remaining 51 units are actually absorbed by the Earth's surface, okay. So this is what we were talking about, the calculation over there. Now from the 51 units which are absorbed by the Earth's surface, okay, is then lost by the Earth's surface by different processes again, okay. So 23 units of the 51 units that is incoming is used up to evaporate water, okay. 7 units is done for again conduction or convection of heating different features on the Earth, okay. So from this 51 units your 23 units are gone, then 7 units are gone, okay, and the remaining of these 51 units are emitted from the Earth's surface, okay. 51 units, from that some part of it is absorbed by the Earth's surface also, and now it is being emitted from the Earth's surface as outgoing infrared radiation, okay, that is also called terrestrial radiation, okay. So this is all done, 100 units, okay. We have got a understanding of how these 100 units are either utilized or it is reflected, scattered back, okay, into the space. But from calculations again, we have found, okay, that Earth actually radiates 117 units away from the surface, okay, not just 21 units remaining, okay. Over here this was only 21 units remaining from the 51 units that we were talking about, okay. So how is that extra kind of units are coming? So from that 117 units, only 6 of these are actually emitted back into the space, okay, and the remaining 111 units are actually the infrared radiation, okay, it's actually emitted to the atmosphere from the earth's surface. So earth again acts as a source of energy, source of some kind of radiation. Okay, so that is what we are saying. So earth then radiates energy out in infrared radiation, and then this again, you know, helps in the energy gain of the earth's surface, and some part of it is again lost into the atmosphere. Again it is absorbed by the atmosphere, some part of it, and some part of it is again reflected back from the atmosphere. So it's like a continuous process. Okay, so if you see this diagram, okay, so your solar energy is coming. Okay, so there will be an energy gain at the earth's surface. Okay, so after the energy gain is there, okay, you will have to understand energy loss of the at the earth's surface. Okay, so there is convection and conduction, okay, that is heating up of different you know, features on earth. Then there is evaporation, okay, and then there is infrared radiation. Okay, so some infrared radiation is, you know, emitted back into the space, and then there is emitted infrared radiation to the atmosphere. Now all these together is actually helping in energy gain by atmosphere also. So when we are trying to understand the energy balance or radiation balance of different components of the earth system, we have to see this. Okay, so we have to take into account energy gain by earth surface, energy gain by atmosphere, energy loss from the atmosphere, as well as energy loss from the earth surface. Okay, so this is what we will be calculating over here. So as I said, so 51 units is the absorption of the solar radiation, okay, and 96 is actually the absorption of infrared radiation, that is again emitted back from the atmosphere. Okay, so this is only at the earth's surface. So this actually comes up to 147 units. Okay, now what are the processes that are causing an energy loss at the earth's surface? As per the diagram that was just shown, so there is heat loss by evaporation of water, so that is 23. Okay, we had already seen from those you know, 51 units which how many units are used up for different processes on the earth. So 23 units is evaporation of water. Then you have 7 units that are used by conduction and convection. Okay, then infrared terrestrial radiation emitted to space. We saw from that, you know, the 117 units of infrared of you know, in radiation units, okay, which are given by the earth, okay, which is emitted by the earth. Okay, out of those only 6 units are actually emitted back into the space, and then the infrared radiation that is absorbed by the clouds and the gases that are present in the atmosphere. Okay, so that is again 111. Okay, so then the total units of energy lost by the earth's surface. Okay, so we are only talking about earth's surface over here, so that is again 147. So you see that they are balanced. Okay, so there has to be a balance, there cannot be more energy lost than what has been gained. So this exercise kind of, you know, helps us understand all the different processes and how the energy balance is maintained. Okay, now we did earth's surface, now we will consider earth's atmosphere. So for earth's atmosphere, going back to what we have already discussed, absorption of solar radiation by atmosphere. Okay, so we are again talking about the energy gain in the atmosphere. Okay, so absorption of solar radiation by the atmosphere from the units that are incoming. Okay, so those are 19 units. Okay, then absorption of infrared terrestrial radiation by the atmosphere. So over here, if you remember, we had you know, talked about infrared radiation, terrestrial radiation that is absorbed by atmosphere. Okay, so the similar units are going to be mentioned here. So it's the same process that we are talking about. Okay, latent heat released by condensation of water vapor. It is similar to the process that we had talked about, where the earth's surface loses energy, okay, due to the evaporation of water. So that is again 23 units. Okay, and then sensible heat release by convection and conduction. We had also talked about this process where the energy loss is happening when we are considering the earth surface. So that is 7 units. So the total units is actually going to be 160. Okay. Now how does atmosphere lose the energy? Okay, it can gain and it has to lose the same amount of energy. So infrared radiation emitted to the earth, okay, emitted to the earth from the atmosphere. Okay, so that is 96. Now this process is similar to the absorption of the solar radiation, okay, by the earth's surface that we had talked about in the previous slide. And then some amount of infrared radiation is emitted to the surface. Okay, so that is actually 64 units if you calculate the processes. Okay, again in the previous slides, the units that are mentioned, if you calculate for each of the processes, you get 64, and that is total is 160. Again you see that there is a balance over here. Okay. So now when we consider the total radiation balance of earth's surface and atmosphere, okay, so all the processes combined together. So absorption of solar radiation at earth's surface, okay, it's again 51. We know that 51 units are, you know, kind of absorbed by the earth's surface, okay, and the absorption of solar radiation by the atmosphere. Okay, so totally we are now trying to understand the energy gain due to the absorption of solar radiation at earth's surface as well as the atmosphere. Okay, so we have 51 and 19 and the total is 70. Okay, now the processes that are causing an energy loss at both the earth's surface and in the atmosphere. Okay, so in that the infrared radiation that is emitted from the earth's surface to space is 6 units. Okay, and the infrared radiation emitted from earth's atmosphere to space again is 64. Okay, so total is 70. So this actually proves that there is no net gain or loss of energy, and then the earth's average temperature should be remaining constant. Okay, now the entire understanding of how global warming and climate change is affecting us is where this balance, okay, when this balance is upset, okay, it goes towards say maybe more energy is being gained by us. Okay, so that is when the climate change is actually going to start, or like, you know, it is actually going to intensify. Okay, if this balance is disturbed in any way. So if this fragile balance tips, okay, so if it gains as we are seeing right now, that the energy gain is more, and due to that the heat is also, the, you know, the heating of the earth's atmosphere and earth's surface is also getting, it's increasing. Otherwise, like during ice age, that we see that the the loss of energy, or the, you know, the incoming energy is not enough, okay, to heat up the atmosphere or the surface, or which helps in raising the temperature. Okay, if that is more, then obviously the global atmospheric patterns, the weather patterns, the climate patterns, everything is going to change. Okay, so understanding energy, earth's energy budget and the radiation balance is important in this aspect. Okay, for this reason. So obviously the electromagnetic radiation, in the case of, you know, the wavelengths of the energy that are actually, that can be absorbed by the earth and that is not, you know, being
मैम
absorbed. Yes.
देयर इज वन क्वेश्चन मैम,
Okay.
जैसा आपने बताया कि एनर्जी बैलेंस होता है अर्थ का,
Hmm.
तब वी नाइदर गेन एनर्जी नॉट, मतलब जितना गेन करते हैं उतना लॉस्ट कर देते हैं।
हाँ.
तो अर्थ में आइस एजेस क्यों आती हैं, या हम कहते हैं कि अर्थ का टेम्परेचर टाइम के साथ बढ़ रहा है, इंक्रीज हो रहा है।
हाँ, तो
तो
यही चीज़ है ना कि वी हैव टू, मतलब ये बैलेंस मेंटेन होना चाहिए था। पर जैसे जैसे आप अगर ग्रीन हाउस गैसेस के अमाउंट बढ़ाते जा रहे हो, तो ठीक है, तो ज़्यादा हीट उसमें ट्रैप हो जा रही है। सो दी
जी
प्रॉबेबली द इंफ्रारेड रेडिएशन जितने यूनिट एक्चुअली स्पेस में एमिट होने चाहिए थे वो एमिट नहीं हो रहा है, वो अब्जॉर्ब हो जा रहा है। तो वही मतलब वो बैलेंस समझाने का यही है कि बैलेंस में मतलब ये थियोरेटिकली बैलेंस में होना चाहिए,
मैम,
पर
जो
अब नहीं
अभी
है।
हम लोगों ने स्टडी किया, जो
हाँ
डिस्कशन अभी हम लोगों ने किया, ये मतलब थ्योरेटिकल डेटा है
हाँ
कि ऐसा ऐसा होना चाहिए
हाँ।
कि शुड बी बैलेंस्ड, शुड बी बैलेंस्ड, बट एक्चुअली दिस इज नॉट,
नो। सो यू
ऐसा
कैन
नहीं
सी
है।
कि जैसे हम बात कर रहे थे ना, 100 यूनिट्स आया और उसका हमने प्लस माइनस करके अब्जॉर्प्शन कहाँ हुआ, रिफ्लेक्शन कहाँ हुआ, स्कैटरिंग हो गया, वो सब मिला के हमको 100 यूनिट्स का कैलकुलेशन मिल गया। उसमें से हमारा था कि रिमेनिंग 21 यूनिट्स ऐसा कुछ अर्थ में अब्जॉर्ब होना चाहिए और अर्थ उतना ही रेडिएट करेगा। पर हमने
जी
बाद में देखा कि अर्थ एक्चुअली 117 यूनिट्स कर रहा है। ठीक है, तो उसका मतलब क्या हुआ, वो जो इंफ्रारेड रेडिएशन है, जो टेरेस्ट्रियल रेडिएशन की हम बात कर रहे थे, ठीक है, वो एक रोल प्ले करता है। ठीक है, तो मतलब उसमें रोल में आते हैं, तो आपके ग्रीन हाउस गैसेज आ जाता है। ओके, आपका अर्थ पे भी ऑब्वियसली द अमाउंट ऑफ वाटर और अमाउंट ऑफ स्नो, दैट इज ऑल्सो प्लेइंग अ रोल ओवर देयर। Okay, so either they will reflect back the if there's snow, more snow, most of the radiation will be reflected back. But if it's water, okay, or if it's barren land, then most of it will get absorbed, and then again it will be reflected back as infrared radiation. Okay, and if the gases are more, then that infrared radiation actually वो absorb कर लेगा, वो पूरा पूरा एनर्जी बाहर जाने नहीं देगा।
यस मैम, तो
हाँ।
ये मेरा क्वेश्चन है कि इसमें ह्यूमन का रोल क्या है? जैसे हम लोग पैटर्न देखते हैं ना,
हम्म।
तो बहुत सारे ग्लेशिएशन पास्ट में भी हुए हैं,
हम्म।
हिस्ट्री में भी हमारे बहुत सारे एजेस आए हैं।
हम्म।
तो जैसे, या फिर हम ऐसे कहते हैं कि ग्लोबल वार्मिंग हो रही है, तो
हाँ।
ऐसा नहीं है ना हिस्ट्री में कि पहली बार हो रहा है, ऐसा भी
नहीं
बहुत बार
नहीं
टेम्परेचर नहीं हुआ है।
नहीं, बात वही
इसमें
है कि
हमारा कितना रोल है?
हाँ, तो इसमें ह्यूमन कंट्रोल यही है कि जो नेचुरली जिस मतलब रेट पे पहले हुआ है, ठीक है, आप पिछले आइस एजेस या उसके बारे में भी पढ़ेंगे, वो एक झटके में नहीं आया है, या जो टेम्परेचर राइज है, अनलेस एंड अनटिल देयर हैज़ बीन अ वेरी बिग इवेंट, जैसे जो हमारा केटी बाउंड्री जो हम बोलते हैं, ठीक है, वहाँ पे इतना ज़्यादा हीट डेवलप इसीलिए ही हुआ था क्योंकि
वोल्केनिज्म।
हाँ, a lot of volcanism, concurrent volcanism happened all across the globe, and together they raised the heat of the earth's surface and the earth's atmosphere. Okay, now that was a naturally occurring thing, and we also saw that a lot of species got extinct.
जी मैम।
हाँ, तो वो एक नेचुरल प्रोसेस है। फिर उसके बाद आपका आइस एज आया। आइस एज भी इट द स्पैन ऑफ द आइस एज वाज वेरी लॉन्ग। ओके, एंड वो जो वोल्केनिज्म के बाद जो कूलिंग पीरियड या वो जो हीटिंग पीरियड है वो भी काफ़ी लंबा था। अभी ह्यूमन ईयर्स के हिसाब से दैट इज 10 टाइम्स 100 टाइम्स मोर, बट राइट नाउ इन ह्यूमन ईयर्स वी कैन सी दैट द temperature, the increase in temperature in the last century or the century before, okay, the rate is increasing. So human influence यहाँ आता है कि हमारे जो एक्टिविटीज़ है उससे ये नेचुरल फिनोमेना की सारी रेट्स बहुत ज़्यादा बढ़ रही है। तो जो मतलब एक एग्जांपल बाद में भी होगा कि कोसी रिवर, ठीक है, आपने सुना होगा कोसी रिवर की वजह से बिहार में बहुत सारे फ्लड्स होते हैं, and
जी
the
मैम।
reason for it is that it keeps shifting, okay, owing to the kind of the land that is there, and the sediments over there. We will learn about this when we are talking about fluvial geomorphology, but छोटा सा एग्जाम्पल। तो ठीक है, तो ये बहुत सालों से अरसों से चला आ रहा है, ये होता ही है ये। पर अब क्या है, वहाँ पे सेटलमेंट्स बिल्ड हो जाते हैं, तो वहाँ पे प्रॉपर्टी लॉस होती है, ठीक है, और व्हेन यू डू सैंड माइनिंग, ओके, सो यू आर रिमूविंग मोर एंड मोर लैंड फ्रॉम देयर और सैंड फ्रॉम देयर, सिल्ट फ्रॉम देयर। सो क्या होता है कि नदी को फिर ज़्यादा स्पेस मिलता है और वो ओवरफ्लो तो होगा ही, बिकॉज दैट इज़ द नेचर ऑफ
जी
द रिवर। बट वही हो रहा है ना कि आपका लैंड डिग्रेडेशन हो जा रहा है वहाँ पे, तो रेट बढ़ गई है, इंटेंसिटी बढ़ गया है, हार्मिंग कैपेबिलिटी बढ़ जाती है। तो ग्लोबल फिनोमेना आज जो चल रहा है वही प्रिंसिपल ऑफ यूनिफॉर्मिटेरियनिज्म जो हमने पिछले हफ्ते मैंने बताया था, वो सेम है कि जो प्रोसेसेस आज हो रहे हैं वो पहले भी होते थे, पर रेट में बहुत डिफरेंस है, एंड
जी मैम।
उसका इफेक्ट्स हमको और बढ़ के दिख रहा है अभी इस समय।
यस मैम।
हाँ, so I hope that clarifies that why the balance, like why we are talking about that balance when it affects or when it is upset, uh, what we are now seeing as global warming, climate change, कि हम अब क्यों हमको उसके बारे में ज़्यादा सोचना पड़ रहा है।
जी मैम, वो रेट फैक्टर करना है,
हाँ,
क्योंकि
रेट
पास्ट में भी
फैक्टर।
हुए।
हाँ
पास्ट में भी ये नेचुरल प्रोसेस हुए, लेकिन वो नेचुरल इवेंट्स की वजह से हुए
हाँ।
उसमें और अभी तो कोई नेचुरल इवेंट नहीं हो रहा है, फिर भी इंक्रीज हो रहा है।
हाँ
सारी चीजों में हम
एग्जैक्टली।
लोग को होता है।
हाँ, तो वो रेट इंटेंसिफाई हो जा रही है, ये बड़ा एक मतलब फैक्टर है जिसकी वजह से वी नीड टू यू नो learn and understand and also try to manage these kind of incidents.
मैम एक क्वेश्चन और है
हाँ।
मेरा। मैम जैसे अभी हम लोग नेचुरली कहते हैं कि हीट अप हो रहा है और
हम्म
हमारा काजेज है, ठीक है। ऐसे ही एक इवेंट जिससे भी है, जैसे मास एक्सटिंक्शन। तो
हम्म
लोग अभी भी प्रेडिक्ट कर रहे हैं कि जिस रेट से अभी भी एक्सटिंक्शन हो रहा है,
हम्म
स्पीसीज गायब हो रही है, तो इट मे बी द एज ऑफ मास एक्सटिंक्शन।
yes, it could be
अभी भी
a, हाँ, it could be an
मास
age of
एक्सटिंक्शन
mass
फेज एक
extinction, yes.
नेचुरल साइकिल हो सकता है।
हम्म
तो ये भी तो हो सकता है कि मतलब हम लोग भले कह रहे हैं हमारा रोल इतना ज्यादा है, ये हो
हम्म
सकता है कि कुड बी द प्रोसेस ऑफ नेचुरल साइकिल, मतलब ऐसे इंक्रीज होना।
yes, it is a natural cycle, but just imagine that beforehand there were not like there was a total loss of extinction, मतलब loss of species नहीं थे. Suppose mass extinction, I forgot the criteria for what we call mass extinction. There's a percentage of species, okay, that will be lost when it is called a mass extinction.
जी मैम।
Okay, so right now naturally the species they evolve, they try to avoid that extinction phenomena for them. Okay, so that is natural again. बट वाई वी आर एक्चुअली थिंकिंग अबाउट इज कि हम एक्सटिंक्ट नहीं होना चाहते हैं ना। अब जो हम रैशनल दिमाग वाले हैं, ठीक है, वी नो हाउ व्हाट थिंग्स आर, वी आर स्टडिंग एवरीथिंग, सो वी आर ट्राइंग टू अवॉइड दैट मास एक्सटिंक्शन, वी वांट टू स्लो इट डाउन एज मच एज पॉसिबल। प्रोसेस नेचुरल है, पर हमें,
मे बी।
हाँ,
तो
हमें
ये तो
उससे
ऐसा हुआ ना
प्रॉब्लम
मैम
है।
कि वी आर ट्राइंग टू कंट्रोल द नेचुरल थिंग्स विच आर
एग्जैक्टली।
एक्चुअली वर्किंग,
हाँ,
तब
तो
उसमें तो।
हाँ वही बात है ना, समर विंटर सब तो नेचुरली है, ठीक है, पर वी आर यूजिंग हीटर क्योंकि हमको नहीं चाहिए, वी डोंट वांट डिस्कम्फर्ट। सो इट्स द सेम थिंग, वी एज ह्यूमंस वी हैव प्रीवियसली ह्यूमंस वर इन सिंक विद द नेचर, तो जैसे जो हो रहा है वो करना है, पर जैसे जैसे डिमांड्स बढ़ती है तो सप्लाई भी उसके वजह से बढ़ रही है, और हमारा दी वांट फॉर
स्टडी जो
कंफर्ट।
जो हमारा स्टडी भी है उसी में जा रहा है कि जिससे चीजें कंफर्ट में हो।
हाँ, तो
जी मैम।
इसीलिए तो अब वही है, बैलेंस उधर हट रहा है बिकॉज वी आर एक्सप्लॉइटिंग अर्थ एंड रिसोर्सेज टू मच फॉर आवर कंफर्ट, एंड वी आर पुटिंग एवरीथिंग एल्स एट रिस्क। तो ये चीज ये नेचुरल नहीं है ना, बिकॉज नेचर नोज हाउ टू रीसेट एंड देन अगेन क्रिएट।
यस
बट
मैम,
इफ,
जैसे मैम आपने
हाँ,
वो कोसी रिवर वाला फैक्टर बताया कि वहां तो नेचुरल प्रोसेस होता है, बट वहां जो एंथ्रोपोजेनिक एक्शन होते हैं उसकी
हाँ
वजह से वो उसका रेट बढ़ जाता है।
हाँ
वो चीज हम सोचते हैं कि नेचुरल प्रोसेस जैसे हो रहा वो हो, लेकिन हम अपने कितना रेट को कम कर सकते हैं, मतलब
हाँ
खुद से किस चीज को कितना प्रिवेंट कर सकते हैं।
हाँ
हम लोग उस चीज पे स्टडी करके कम कर रहे हैं।
हाँ, वही चीज़ है, तो अब वो कैसे कम कर सकते हैं, हाउ कैन वी प्रिवेंट इट और मैनेज इट, फॉर दैट ओनली वी नीड टू नो हाउ दीज प्रोसेसेस आर वर्किंग, व्हाट कैन बी
जैसे
डन, कि अगर हम यहाँ से इतना सैंड ना हटाए, अगर सैंड हटा दिया तो एग्जैक्टली exactly क्या होगा, और अगर वहाँ पे स्लोप बढ़ा दिया तो क्या होगा, स्लोप घटा दिया तो क्या होगा। तो ये सारी चीज़ें, these things are only actually mostly studied in under earth sciences, सो वही चीज़ है, तो ये कोर्स उस हिसाब से हेल्पफुल है।
जी मैम।
हाँ,
थैंक यू मैम।
ओके, थैंक यू सो मच, दैट वाज अ वेरी नाइस डिस्कशन, थैंक यू फॉर दैट क्वेश्चन एंड गिविंग मी द अपॉर्चुनिटी टू एक्सप्लेन। ओके, So coming back, so again electromagnetic radiation, why we need to know is that the greenhouse gases, okay, that we talk about, you have CH4 and CO2 and then you have water vapor, okay, so ये जो है ठीक है, they are mentioned in this on the slide also, okay. So how they play a role is that they absorb or they reflect certain wavelengths of electromagnetic radiation, okay. So for the greenhouse gases that are present in the earth's atmosphere, okay, so they radiate long wave radiations back to the surface and to space as counter radiation, okay. So long wave radiations, so you can see over here, so long wave radiations, ओके सो वेवलेंथ के हिसाब से है, ओके, तो दीज आर लॉन्गर वेवलेंथ, ओके, lower frequency, and these are again higher frequency but shorter wavelength radiations, okay, electromagnetic radiation. Now we know the visible light, okay, so ye like the wavelength, the electromagnetic radiation under this wavelength range is actually we get it, it's incident on the earth's surface, okay, and some part of this long wave radiations, okay, so these interact with your greenhouse gases also, okay. So the sun emits radiation at all wavelengths, okay, and most of large part of that radiation actually falls in the visible light wavelength. So you have from I think 730 nanometer to for around 380 nanometer. This is the range, the exact. Okay, so you can consider from 700 to 400 nanometer approximately. Okay, so this is the range of the wavelength that is under visible light, and most of the solar radiation is also falling under this wavelength range. All the long wave radiations are the important ones to understand the greenhouse effect. Okay, so the greenhouse effect, as you can see, okay, for example, sorry, yeah. So this is your a greenhouse is where you have plants, and then they are enclosed in a glass kind of a shelter, okay. So over here the solar radiation, and then you have 1 2 3, okay, all these are different wavelength of radiation, okay. So the red one is your long wave, the orange one is your short wavelength, and the green one is your visible light, okay. And then you consider this the glass house as your atmosphere, okay. So the first process we are going to talk that the long wavelength infrared light, okay, is actually reflected by the glass, okay. So it comes through the atmosphere and some part of it is reflected back, okay. So the next process, the B process, okay, the visible and short wavelength infrared pass through the glass, okay. So some part of the short wavelength infrared light and the visible range, okay, of the electromagnetic radiation actually passes through the atmosphere. Then you have the process C. So process C is where your short wavelength infrared light is absorbed, and then it is re-emitted as long wavelength infrared, okay. So over here you can see at C the wavelength range changes, okay, from short infrared it turns into long infrared, okay. So when I am saying short infrared, short wavelength infrared and long wavelength infrared, okay. So you can see now for D, the visible light that passed through your atmosphere is now reflected back into the reflected back from the earth's surface, okay. It is again, it can pass through your atmosphere also, okay. Now your F process, okay, your D and E deal with the visible one. D is where your visible light is getting reflected, and your process E is the reflected visible light is passing through your atmosphere again, Okay, now the long wavelength infrared that was kind of reflected back from the Earth's surface due to the process C. Okay, it now gets reflected back by the atmosphere. Okay, and then this long wavelength infrared radiation actually it undergoes multiple reflections from the atmosphere. Okay, so this long wavelength infrared is actually trapped inside the greenhouse. Okay, that means that it is trapped between the atmosphere and the earth. Okay, now this radiation is actually causing the rise in the temperature. Okay, due to the multiple interactions that it has. So if, like, as the effect of the atmosphere is that, or the role that the atmosphere plays actually is that it does not let your long wavelength infrared light actually pass through it. Okay, so that is why if your long wavelength infrared light is not coming into the atmosphere, that is fine, that is good. But this conversion, okay, of the short wavelength into long wavelength, and then the interaction of this long wavelength infrared light with the earth's surface and the atmosphere, that actually causes the, that is called the greenhouse gas effect. Okay, that is called the greenhouse effect. Okay, so the glass, now you think in terms of that the glass is the earth's atmosphere. Okay, so that is what we understand. So that is why we say that the greenhouse gases actually trap the heat. This long wavelength radiation is actually causing this rise in heat. So again, that's where even your albedo effect again comes into play. The light and the heat, we had already discussed about this. So now we come to the effects of this kind of different things that we saw, the radiation balance, earth's energy budget, and also greenhouse effect, albedo effect, all these interacting together any which way causes climate change at global scale. Okay, but the most important factor right now that most of the things that we have to concentrate on is the human influence. Okay, so the human influence. So the one of the biggest causes that we see in the increase of say greenhouse gases, okay, is fossil fuel combustion or fossil fuel use. Then you have deforestation and agriculture, including livestock rearing and also using fertilizers. Okay, so anything that causes the increase in the amount of greenhouse gases that are being created, from the Earth's surface and then adding up to the Earth's atmosphere. Okay, so together they are actually causing an increase in greenhouse gases. Okay, which increases the global warming and causing the resultant climate change. And an increase in CO2 additionally also causes ocean acidification. Okay, so that actually leads up to coral bleaching, okay, that we know, and also loss of some other calcium containing or calcium like the living creatures that have calcium in their composition or their structure. Okay, so these two or these few species actually are very adversely affected when there is ocean acidification taking place. Now you can see that the effects are multiple. Okay, some are at a lower uh, you can say observed at lower rate. Okay, some are actually kind of causing a domino effect, like one change is going to cause a change in the another system and then another system. Okay, so uh, you these range from extreme weather in events, then you have frequent occurrences of natural disasters, like you have cyclones and typhoons and hurricanes. Okay, and you can see that there is rise of epidemics. Then you have worse crop failures, you have droughts and diseases that are happening in livestock, okay, which is transferred to humans. So all these are either individually, as a result of some of these causing factors, the global warming causing factors. Okay, otherwise they all are actually very intricately related to each other. Okay, and that is why uh, it is important to try to reduce the human influence or human effects on the rise of the global warming, or to causing the global warming for that matter. Okay, so and then the most the byproduct of this global warming and climate change is water vapor increase. Okay, then your release of methane into the atmosphere, and then reduced reflection of solar energy. The albedo effect that we talked about, this is due to the greenhouse gas effect. Okay, it is going to cause, and also water vapor is also part of the greenhouse gases. Okay, so these three together is going to increase your greenhouse gases again, and then also increase global warming. So it's a feedback loop. Okay, so there is mostly positive feedback. So it is only causing increase in greenhouse gases and global warming and climate change. So we have to try to control this cycle as much as possible, and to do that we need to also understand the concepts of the different processes that are actually causing some of the naturally occurring processes. So a quick view about carbon footprint. Okay, so the way that we can kind of measure the uh, mm, measure the role that an individual or a kind of industry or a nation or globally we play, the role that we play, okay, in contributing to this global warming, or kind of decreasing our contribution to this global warming. So carbon footprint is one of the way where you can measure the impact, okay, that our activities have on the environment, and obviously in particular to climate change, because we are talking about it. So it kind of covers your production of greenhouse gases at individual level, as well as the bigger kind of company or nation levels also, and how we contribute to the increase in greenhouse gases, and either in our day to day life, like burning fossil fuels, or heating and transportation. These factors play a role in how we can uh, measure those impacts. Okay, so the way we can these are some of the components, okay, so that are considered when we are talking about carbon footprints. You have the consumption of fuel, the water management that we can have, the increase or decrease in CO2 emissions, CH4 emissions, then production of electricity, wastage of electricity, and how much resources we are using to produce electricity, then usage of gas, and kind of again the resources that are being used for that, and how much we are actually recycling uh, to try to offset the other offset our consumption, and how the waste is managed, and how how much of emissions we are causing due to transportation. Okay, so carbon footprint, this is some of the factors, or some of the aspects of it. Then how can we reduce carbon footprint? Okay, so at least at individual level, there are some things that we can do. So as a lot of government owned properties, like you have airports, railway stations, as well as educational institutes. Okay, so they are trying to shift more towards the solar powered electricity generation. Okay, then you can reuse, recycle, reduce. Okay, these three R's are very important to try to reduce your carbon footprint. And also, kind of giving more focus, or more support to local businesses, local food businesses, or your local farmers, and try to recycle, or buy second hand items. So these are some of the ways where you can reduce. Now these are carbon footprints. Okay, personal carbon footprints, or at an institute or a company or a government kind of levels that we can do. Now, as a globe, okay, a globe with multiple nations, uh, some kind of agreements, and some global institutions have been put into place to try to bring down the effects of climate change at a collective level. Okay, so I think the oldest known kind of such an agreement that was signed between I think more than 190 nations was like Kyoto Protocol. So it was it was put forth in 1997, but in 2005 it was kind of accepted and signed by a number of nations. Okay, so Kyoto Protocol was kind of like the first step towards uh, accepting that climate change is happening, and also nations taking responsibility of it, and where the first time reduction in emissions, okay, were targeted within a range of years. So Kyoto Protocol was like the the starting block, where after that we have a lot of conferences, and kind of different agreements which are important when trying to tackle climate change. And the also one another important one is the 2015 Paris Agreement, where like as per the news also, that India has played a very important role, and India also took a lot of kind of it put it mentioned that they would we would be as a nation targeting a few things where we would be reducing our carbon footprints, and try to achieve the reduction of emissions, and also increasing our solar capabilities, solar power generation capabilities. Okay, so these are some aspects of reducing carbon footprint, and in like also tackle climate change at global levels. So now,
चलो,
yes,
एक क्वेश्चन।
yeah,
अच्छा मैम, ये तो सही है कि ग्लोबल वार्मिंग के लिए सारे कंट्रीज जो हैं वो रिस्पॉन्सिबल हैं,
hmm,
मोर और लेस, सारे डेवलप्ड और अंडर डेवलपिंग।
hmm,
जैसे ये फैक्टर आता है कि सारे, मतलब सारे कंट्रीज इस पे सारे अपना जो फॉसिल फ्यूल है
hmm,
उसको रिड्यूस करें, मतलब अपनी कुछ चीजें। लेकिन जैसे मैम कुछ कंट्रीज हैं, जैसे इंडिया है,
hmm,
तो इंडिया भी डेवलपिंग कंट्रीज है,
hmm,
बट अमेरिका क्या है, वो डेवलप्ड कंट्रीज है।
hmm,
तो वो अगर उसको ये चीज करनी होगी तो अपनी टेक्नोलॉजी को शिफ्ट कर सकता है वो सोलार पे या
हाँ,
दूसरे एनर्जी सोर्सेस पे।
hmm,
बट इंडिया को अगर तुरंत करना हो तो ये चीजें टफ है, क्योंकि अभी भी हम रोड्स पे देखते हैं
हाँ,
तो
हाँ,
मोस्ट ऑफ द जो गाड़ियां हैं वो फॉसिल फ्यूल पे ही चलती हैं। अभी
hmm,
इलेक्ट्रिक बाइक्स यहाँ अयोध्या में भी जल्दी आ गई है,
hmm,
बट मोस्ट ऑफ द चीजें जो है वही की हैं।
hmm,
लेकिन अगर जैसे मान लीजिए आज ठीक है एग्रीमेंट्स, ठीक है, मान लीजिए कल को अफ्रीका है, अफ्रीका इनिशियली तो उसके पास टेक्नोलॉजीज आ नहीं जाएंगी। अगर
hmm,
वो अपने आप को डेवलप करना चाहे और अपने फॉसिल फ्यूल्स को यूज करने लगे तो
hmm.
उसके लिए क्या करेंगे? ऐसे सारी कंट्रीज को एक साथ कैसे लेके हम चलेंगे आगे?
देखिए, तो ये एक्चुअली रिसेंट में जितने भी अग्रीमेंट्स या ये सीओपीज होते हैं, कॉप्स होते हैं, उनमें ज़्यादातर कुछ कुछ ऐसे मतलब रूल्स नहीं बोलने चाहिए, कुछ कुछ ऐसे एग्रीमेंट्स हुए हैं कि मतलब दी अंडर जो डेवलपिंग नेशंस है, ठीक है, इन पे ज़्यादा भार ना दिया जाए अभी के लिए, ठीक है, क्योंकि अभी भी टेक्नोलॉजी हमारे यहाँ पे उतना डेवलप नहीं हुआ है कि हम प्रोडक्शन स्केल में उसको लाएं। अभी भी
जी
ये जो
मैम।
हम सोलर पैनल की बात करते हैं या जो है, ये बहुत कम जगह पे ही है, क्योंकि इसकी प्रोडक्शन, हमारे पास प्रोडक्शन कैपेबिलिटी नहीं है। और उसके ऊपर जबकि सोलर पावर जनरेशन हमारे लिए सबसे इजी है, इवन फॉर अफ्रीका इट इज़ ईजियर बिकॉज वी आर ट्रॉपिकल कंट्रीज एंड
जी जी मैम।
अफ्रीका इन इटसेल्फ इज़ एन इक्वेटोरियल कॉन्टिनेंट, ओके। सो हम वहाँ पे फोकस ज़रूर कर रहे हैं, पर वही चीज़ है कि हमारे पास इतनी प्रोडक्शन कैपेबिलिटी नहीं है कि हम हमारे डे टू डे लाइफ में उसको ला सकें। तो इसके लिए वो जो टाई अप्स होते हैं, स्टार्टअप्स होते हैं, ऑल्सो दी काइंड ऑफ फंड्स दैट वी रिसीव, दैट इज़ हेल्पिंग, वो डेवलप्ड कंट्रीज से ही हमको मिल सकती है। तो डेवलप कंट्रीज़ को वहाँ पे रिस्पॉन्सिबल या फिर अकाउंटेबल हम होल्ड कर सकते हैं कि जितना भी अभी एक्चुअली टेम्परेचर रेज हुआ है वो उनकी डेवलपमेंट की वजह से है, हमारी डेवलपमेंट उतनी हुई नहीं है कि हम इतना एमिशन करें। ये
जी
एक
मैम।
बात है, हाँ। तो फॉसिल फ्यूल्स यूसेज तो हमारा एकदम से कम नहीं हो सकता है, वी कैन ओनली शिफ्ट स्लोली टू रिड्यूस आर डे टू डे डिपेंडेंसी ऑन इट,
यस
as
मैम।
per like cleaner fuels when we are using say if we don't use coal, मतलब चूल्हे वाला कोल को हम नहीं यूज़ करें, ठीक है, एंड वी ओनली यूज़ इलेक्ट्रिकल काइंड ऑफ और पाइपलाइन गैसेस which are supposedly cleaner fuels for us. Okay, so what we are doing, that individual dependency on coal is getting reduced, okay, and coal is only being used to generate electricity for now. So वहाँ पे पर्सनल कार्बन फुटप्रिंट थोड़ा कम हो जा रहा है, ठीक है, ये एक चीज़ जो हो सकती है।
अवेयरनेस और दूसरी चीजें भी इसमें फैक्टर करेंगी।
हाँ हाँ, तो ज़रूर, तो जैसे फॉर नाउ आई इन द रिसेंट आई थिंक न्यूज़ वाज दैट वी आर टारगेटिंग सम 1 crore households to have solar power, solar powered electricity, I think, by
यस मैम, ये
2047.
राजस्थान में भी सोलर का बहुत बड़ा प्रोजेक्ट चल रहा है
हाँ
मैम, उसी के लिए एनर्जी प्रोडक्शन के लिए।
हाँ, तो ये सारी चीज़ें डेवलपिंग नेशन कर पा रही है because of kind of some funds that we get from the developed nations, also from these agreements and these international kind of conferences. And there is also buying and purchasing of I forgot that block, मतलब वो एक नाम होता है उसका, it's like a trading, okay. If I'm emitting this much of emissions, okay, so either you buy those emissions from me and you try to settle your targets according to that. Every nation has some target. Okay, so there is kind of buying and selling of these green tradings also. uh, I am not very clear about this, but there is a concept like this also available. So these are very soft kind of ways how at an international level we are trying to tackle climate change.
जी मैम।
कितना ये ऑन द ग्राउंड लेवल तक हम कर पा रहे हैं, ये देखना तो मतलब काफ़ी मुश्किल है, एक ओवरऑल आइडिया ही है। अब जैसे मैं यहाँ हूँ, आईआईटी में हूँ, तो हमारे हॉस्टल में सोलर जनरेटेड इलेक्ट्रिसिटी है एंड वी आर काइंड ऑफ यूजिंग इट, बट एट द सेम टाइम इफ माई कंसिडर माई हाउस, वी आर स्टिल dependent on the general way that electricity is produced for thermal
यस
power
मैम।
plant and all. तो जब तक वो प्रोडक्शन स्केल इंक्रीज नहीं कर पा रहे हैं हम ऑफ दीज रिन्यूएबल एनर्जी सोर्सेज, तब तक फॉसिल फ्यूल की डिपेंडेंसी रहेगी। तो जितना ये डे टू डे डिपेंडेंसी हम कम कर सकते हैं तो उतना अच्छा होगा, at least to try to offset whatever damage that has already been done, at least some part of it.
जी मैम, मतलब टेक्नोलॉजी जो है वो एकाएक नहीं बल्कि स्लोली स्लोली उसको करके हम रिड्यूस कर
हाँ
सकते हैं।
हाँ, और इसमें ही सबसे ज़्यादा रोल डेवलप कंट्री यहाँ प्ले करती है कि दे हैव टू हेल्प द डेवलपिंग नेशंस
Share their technologies.
yes share the technologies and try to kind of help us in increasing the scale of the production and scale of implementation of these technologies.
जी.
Yes. So till now we have tried to understand what are the what is the role of solar radiation, at least for now, the solar radiation and Earth's energy balance in kind of the role they play in the climate on the Earth's climate. Now there are some inherent factors that we do not have any control on whatsoever. Okay, so that is due to the Earth's motion. So as we know, Earth rotates around its own axis and it revolves around the sun. So these two motions play an important role in the uh, seasonal variation as well as annual variation and also variations at longer of longer durations. Okay, so for Earth's rotation, okay, so 24 hours. So some of the effects that we see due to this motion is your day and night. And why we are saying day and night, your temperature differences of the day and night also it varies. Okay, and then you have fluctuating air temperature again due to the rotation itself and so because of that you have differences in the temperature of day and night. And then you have Coriolis effect. Coriolis effect is since we know that the earth is rotating from you know west to east. Okay, so this is the rotation. So due to this rotation, okay, so there are two kind of uh, motions that we see in the two different hemispheres. Okay, so suppose we consider this point on the earth. Okay, so since the earth is moving from west to east, okay, so in that sense if I am visualizing the earth, okay, rotating from west to east, okay, rotating like this point will appear to be moving in this direction. Okay, and if there is a point here, okay, so over here the movement will be in this direction. Okay, so this point, okay, so we are only considering the point. Okay, so the point will move in this direction, so point has moved towards your left. Okay, but the rotation is towards the right. Okay, so this is Coriolis effect, and due to this the currents that we see, okay, oceanic currents or your wind directions, okay, these are dependent on your Coriolis effect. And then due to the earth's rotation, another important effect that we see is tides, the creation of tides, your high tides, low tides, neap tides, spring tides, okay, the different kind of tides. So this is the influence of earth's motion, okay, earth's rotation. Now when we consider both earth's
Ma'am, Coriolis effect. Please explain once again.
huh, okay, so as I said the earth is moving, okay, in this direction, west to east, so consider it's going on right. Okay, so now the earth is moving. Now if we only consider this as a like a reference point, okay, so the reference point is like this. Okay, so it is moving like this. Okay, the point will be the point that was located here has now moved here because this will come over here. Okay, so any object, suppose you have a ship. Okay, I'll just clear these pen marking once again. Yeah,
Yes, ma'am.
yeah, I'll just explain it. Okay, so suppose you have a ship. Okay, you have a ship that is traveling. Okay, same direction. Okay, so due to this movement, okay, this movement, okay, this slowly actually turns like this. this is actually, anything that is moving, okay, will turn. And if there is a ship that is moving in this direction, it will actually slowly move downwards. This is the
Yes.
effect of the this earth's rotation. Okay, anything, any reference point that is there, okay, it moves in a different direction. If the it is stationary, okay, if this is stationary, so there is no issue. But if this is also moving, then there is a difference in the direction of it. Okay, now if we consider your southwest monsoon, okay, as an example, where your Coriolis effect is, very much you can understand. So over here there is, obviously in this there is no India. Okay, so if suppose this is your India, okay, and the rotation is in this direction. Okay, so your wind is moving like this. Okay, your southwest monsoon winds. Okay, this is moving here. Now, if there was no Coriolis effect, okay, so it would have gone straight. It wouldn't have reached the Indian subcontinent. Okay, but due
Yes,
to
ma'am.
this effect, okay, where this is also moving, this will slowly turn upwards. Okay, because now it is turning upwards. Now, if it is moving constantly forward, that is when it reaches India. Okay, this is where your Coriolis effect, it has an effect on the seasons and the weather.
Yes, ma'am.
Yeah, this is understood. Now, if there is some, this is in the northern hemisphere. Okay, now in the southern hemisphere, due to this same, kind of rotation, it has a different route. The wind will follow a different route. It will go towards the, it will move towards your southern side. So there is an opposite kind of a, effect because of this Coriolis effect, because of the Earth's rotation.
Yes, ma'am.
Okay.
I got it.
Okay. So that was only the influence of Earth's rotation. Now we will try to understand the influence of Earth's uh, revolution as well as Earth's rotation. Okay, so there are some kind of terms that we need to understand. That is, first is what is perihelion and what is aphelion. Okay, so perihelion is actually the shortest distance between Earth and the Sun. Okay, uh, on its elliptical orbit. Okay, so the Earth follows an elliptical orbit around the Sun. So perihelion is where it is closest to the Sun. Okay, and aphelion is where it is farthest from the Sun. So you can see even the distance as per the distance, calculated distance. Okay, so on January 3rd, actually the Sun reaches the perihelion point, and July 4th it reaches the aphelion point. So that means at January 3rd it is closest to the Sun, and on July 4th it is farthest from the Sun. Okay, now this perihelion and aphelion, it's not constant throughout say Earth's age. Okay, so this is actually because the change in the eccentricity of the ellipse. Okay, eccentricity is kind of it's a property of an ellipse. Okay, so if the eccentricity changes, okay, this perihelion and aphelion will change. Okay, and because of that, the intensity of your weathers will also change. So if your perihelion distance decreases because of changes in eccentricity, you will have hotter days, you will have hotter summers, and uh, and if the eccentricity increases a lot, then the heat, okay, so the heat from the sun also reduces. Okay, so this is one kind of a factor that also plays on a longer duration, on a longer cycle, that is going to affect your weather. Okay, so the eccentricity of the Earth's orbit, actually the changes happen to in the range of 100,000 years. Okay, so obviously right now the eccentricity that is being followed, that has been there, from like much longer time before. Okay, we probably will not see any change in the eccentricity as per the kind of the duration that it follows. Okay, another factor that plays a role in that is kind of an effect due to the earth's motion is, we know that the earth is actually, the earth's axis is tilted, okay, compared to the ellipse that it follows. Okay, so the axis is like this, it is not perpendicular. So this tilt, okay, so this tilt also has an effect. Okay, this tilt is the reason why uh, there are times where a larger part of northern hemisphere is getting the sunlight, and smaller part of southern hemisphere is getting the light. If it was not there, if the tilt was not there, so it would have been half, western half or eastern half of the entire earth receiving sunlight at one point of time. Okay, then again the way you have your the seasonal variations would have been different. Okay, so there is a control. Okay, there is a control for with regarding each and every aspect of the earth's motion. Okay, so axial tilt also has an effect. Okay, and another part, or another kind of phenomena that we see is the precession of this, precession of this axis. Okay, when the earth rotates, it actually wobbles about its own axis. Okay, so this axis also kind of wobbles. Okay, it follows like a kind of a rotation. Like if you have ever played with a top, so when it spins, it is spinning obviously about an axis, but it also kind of gives off another circular motion, that is called precession. Okay, so earth's axis also precesses. Earth's axis has a tilt, and it also kind of precesses about that tilted axis. Okay, so these are some of the kind of the earth's motion that has a role in the different variations in the say the temperature, the season. Okay, and you can see that due to this tilted axis over here, okay, a larger part of northern hemisphere, as I said, is going to get the sunlight, and a smaller part of southern hemisphere is getting the sunlight. Okay, and due to this there are kind of different days. If you know, you have solstices and equinoxes. Okay, so your equinoxes, where your day and night are of equal duration. Okay, in solstice, okay, one of the either the day or the night is going to be longer compared to the other thing. So your summer solstice is the time where you have I think summer solstice is when the day like it has the longest day of the year. Okay, and the winter solstice has the longest night. Okay, and then you have two equinoxes, you have spring equinox and fall equinox. Okay, so equinoxes happen in March and September, and your solstices happen in, the summer one happens in June and the winter one happens in December. Okay, so these are some of the aspects of Earth's motion. Now there is an important concept called the Milankovitch cycle. Milankovitch cycles is actually he was a scientist, and he found that the uh, due to these three different factors, you have eccentricity, the axial tilt of the earth's axis, and the precession of the earth's axis. Okay, these three phenomena actually have have an effect on the solar heat that is incident on the earth, and therefore it has a direct effect on the variation in the climate of the earth. Okay, so suppose over here you can see like your eccentricity. Okay, right now suppose your eccentricity is at this position. Okay, after 100,000 years probably it will, you know, either shrink. Okay, so then this is going to be the orbit that is going to be followed. Okay, then again you see that the perihelion and the aphelion distance is going to change. Okay, and if that changes, obviously as I said before, the amount of heat also received by the earth will also change. Okay, so this is the effect of eccentricity, and as I said, it is, you know, uh, the duration that has been seen is like, you know, 100,000 years. Now the next one is your tilt. Okay, so the tilt is right now, currently the actual tilt is 23.5 degrees. Okay, so we know, or you know, as you know, it was calculated by Milankovitch that every 41,000 years the axial tilt is going to change. Okay, so either it will, you know, be less than 23.5 or it can be, you know, more than 23.5. So that change can be seen after 41,000 years. And the change in the precession, or the you know, the time that the entire precision kind of the process of the precession will take, or the precessional rotation is going to take, is actually will be around 19 to 24,000 years. Okay, so these were calculated, or these were given forth by Milankovitch, and Milankovitch cycles are important to understand the kind of, you know, the effects of Earth's motion on the climate change. So that's what I said, that these aspects or these effects are not in our control. Okay, these are independent of any human control, and they will be there whether humans are there or not. Okay, and every planet kind of, you know, has a different kind of effect owing to these aspects. Okay, so but knowing this is important is, you know, trying to understand that how far we are from any of the cycles. Okay, so if the axial tilt changes, then we can know that, you know, how much of the northern hemisphere is going to get more heat or lesser heat as per the change of the axial tilt. So it's a conceptual kind of thing, theoretical kind of you know, approach to understand how the climate can change with time, but these durations are very long. Okay, so these are not in the terms of, you know, our average human existence. So the next important thing that is obviously playing a role in the changing you know, landscape of the earth is the hydrologic cycle. Okay, so water is, you know, obviously as we know that 70% of earth's surface is covered by water, and most of it is actually uh, consisted in the oceans. Okay, and 2% is alone is in the ice. Okay, 0.7% is found in the form of groundwater. Okay, and all other surface water bodies, okay, are actually 0.05%. Out of these, you have 60% water contained in lakes, okay, and 33% in the soil moisture, which is actually um, not really obviously usable by us. Okay, 1% is in river and 6% is in atmosphere. So usable water, potable water is actually very, very low. Okay, so that is why water is actually kind of a very important resource for us. Okay, so as living beings, and that is why conserving water or understanding the interactions or the you know, roles different water bodies actually play is you know, necessary for us. So water is, you know, as we say, hydrologic cycle. So that means the water is actually getting cycled through different forms as well as different say bodies. Okay, so the most active cycling of water is actually on the, you know, the top surface of the ocean. Okay, and the shallow level groundwater. Okay, so active cycling as in these are kind of they go through different phases of this hydrologic cycle very easily. Okay, so your surface water and your surface water, like on terrestrial land, on terrestrial part, the surface water and the top few layers or top some depth of the water in the oceans are actually going to play an active role in this water cycle. Okay, and we also try to understand what is the residence time. Okay, so the residence time is important to understand that uh, where the water actually resides for a longer time, and which how much of this can be exploited or utilized for our purposes also. Okay, so the in atmosphere it is, I think, one of the kind of it is very low. The amount of time the water actually stays in atmosphere is pretty low, and the longest one, or the uh, kind of the oldest water, okay, the right now that can be found can be actually in the groundwater, but not the groundwater that is kind of we can extract from. Okay, so it is actually at larger depth, which may or may not be reachable by us. So that is 10,000 years. Okay, so you can see groundwater, the residence time can go from 2 weeks to 10,000 years. So groundwater is actually one of the largest reserves of water that we still have. Okay, and where the water can stay for a longer period of time. And the obviously the shortest one is biosphere in living things, and you have rivers for 2 weeks, lakes for 10 years, oceans for 4,000 years, glaciers and ice caps is 1,000 years. Okay, so these are the different the residence time that we see. So residence time, how do you calculate, is the amount of water that is existing in the reservoir and the rate of addition or loss of the water from the reservoir. Okay, so this is like a basic concept of it. So out of all the water reservoirs that we have, okay, so most important, or at least for the perspective of this course, is the surface water. Okay, so the surface water plays a role in the as we had discussed in the last week's class, was uh, in weathering, erosion, transfer and deposition. Okay, so surface water is the agent that is going to actually do all these or play these roles. Okay, so to understand that, we need to understand like the surface water itself. Like surface water is kind of it is there everywhere. Okay, either in form of lake or rivers, or small ponds. Okay, so now we need to understand surface water in terms of a river, suppose. Okay, so we are considering a river. So there are some you can say land features, okay, that demarcates the extent that a river actually flows through the land. Okay, so that is actually called watershed. Okay, so watershed is the the part of the land where a river actually or a stream system, you can say, is actually draining. Okay, it is actually flowing through that land, and it is going to meet a larger water body later on. Okay, so there can be big watersheds, there can be smaller watersheds. So some parts of the watershed is the divide, drainage divide is like the elevated part that actually divides two different watershed bodies or two drainage basins. Okay, and as we know that every stream has some tributaries. Okay, so that actually feeds into the major or the larger stream, and you can see over here that these tributaries are actually draining water into the larger stream. Okay, and the stream is flowing from the place of where it is originated, and either through glacial melting or a large kind of accumulation point where the precipitation actually holds that water, and then uh, it it helps in the stream being originated, okay, and it is flowing towards a bigger larger water body. Okay, so this entire area is going to be called a watershed. So this is an important aspect of the surface water. And when the surface water is flowing uh, when the surface water is flowing across a portion of the land, okay, so there are two things that are going to affect the amount of water that is actually finally going to reach the larger water body, that is surface runoff and sediment yield. Okay, and the surface runoff and sediment yield, both of these are actually controlled by few elements. So, by few factors. So, you have geologic factors, topographic factors, climatic, vegetation, and as usual, again some part of the human influence, that is in the land use factors. Okay, so geologic factors is, suppose you have rocky terrain. Okay, so there are mostly rocks. Okay, so the water is going to have it needs lot more of energy to cut through the rock and actually flow on the surface. Now if it has alluvium, like we see in Ganga plain, the Indo-Gangetic plains, okay, so over there the stream is going to require a lesser amount of energy, okay, to flow flow on the surface and move from one place to the another. So geological factors happen in this way. Then you have topographic factors. Okay, so elevated land and plain regions, obviously the surface runoff, the rate of it is going to differ a lot. And topographic factor actually plays an important role in the precipitation, for the precipitation. So, most of us have heard about the rain shadow effect. Okay, so your moist, warm air is coming from this direction. Okay, now if it meets an elevated area, mostly a hill range or mountain range, so most of the the moisture is going to be precipitated out here on this part of the on this side of the slope. Okay, and as the air has lost most of its moisture, okay, so the air becomes drier in nature and it will flow towards the leeward slope, okay, the leeward side of the mountain. And the since the air is dry, okay, so it will descend, okay, and it will warm, and actually any water that is going to be present here is actually going to get evaporated due to this dry and warm, sorry, this warmed air, okay, the warmed air. So the this is the issue why there are some places arid regions are created mostly in areas of rain shadow region. Okay, like Tibetan plateau is one example where the southwest monsoon and or the monsoon that is affecting the Indo-Gangetic plain area. Okay, so all the way till there we have good amount of monsoon rains, but due to the presence of Himalayas, okay, so most of the moisture is actually precipitated out, condensed and precipitated out on Indian subcontinent, and very dry air actually reaches the Tibetan plateau, and Tibetan plateau does not get that that the rainfall, okay, and that is why it's a dry and it's not, it's an arid region, okay, and that is why that is called a rain shadow. So Himalayas is a blessing for us because obviously any kind of precipitation is much important for for ecosystem and for our livelihood. So we are on the luckier side because of the Himalayas. So but the anything on the leeward side of Himalayas is going to have is going to be considered as a rain shadow zone. So that's where your topographic factors plays an important role in surface runoff. Okay, and then your climatic factors is obviously if your southwest monsoon winds are not strong enough, or when you have El Nino, La Nina kind of effects. So these are going to have an implication on the seasons and the amount of precipitation that we get. And then vegetation factors is also there. Okay, so vegetation factors has a more control on your surface runoff. If you have if there is deforestation, a lot of water is just going to flow all over the surface and nothing is going to get held down, and a lot of land erosion also takes place if there is deforestation. Then again your agricultural use, or for like irrigation, or for livestock managing. Okay, so a lot of water is going to get used up for that, so the surface runoff can decrease when you build up bad dams, or you put in irrigation facilities. Okay, now since we we have got a
Ma'am,
yes.
please explain climate factors once again.
Okay, climatic factors. So, one of the effects that we see is your El Nino, La Nina. Okay, so these actually kind of affect your continents of South America and Australia. But due to El Nino effect, what happens is you have drier monsoons. Okay, or maybe hotter winters, so that factor is going to affect your precipitation. Okay, and if you have a lower precipitation, then obviously you are going to have less surface water to be used, and for kind of the weathering or erosion that actually should happen because of the surface runoff, and also creation of sediments through the processes of weathering and erosion and transfer and deposition. Okay, so it's a kind of it's a chain effect if your climatic changes happen in that form. uh,
Okay.
yeah, okay, got it.
Yes, ma'am.
Okay, so now we dealt with the surface water, at least the kind of a concept of how surface water is important for the changing of the landscapes. Now we try to understand the subsurface water that is present. Subsurface is actually, the water in subsurface is mostly present in the form of groundwater. Okay, so the groundwater you can actually find in suppose below your surface you have two zones. Okay, so there is a zone of aeration and then there is a zone of saturation. Okay, so zone of aeration is also called the the vadose zone. Okay, and zone of saturation is also called your phreatic zone. Okay, so in the zone of aeration, the top part is actually just moist soil layer is present. Okay, and the vadose, the rest of the vadose zone is actually made up of unconsolidated particles, unconsolidated sediments to be exact. Okay, so sediments are disintegrated form of rocks. Okay, soil and rocks both together, they are also called regolith. Okay, so this part, this vadose part is mostly composed of this regolith or unconsolidated sediments, and these have a lot of open spaces which are filled with both air and water. Okay, but it's a mixture of both. Then you have this water table. Okay, and below this water table level is actually the zone of saturation, where all the open spaces that are present, say either in the rocks or in the sediments that are present at that depth, okay, all the pores are filled with water alone. Okay, zone of aeration has water and air, okay, and zone of saturation has only water in uh, the open spaces that are present. Okay, and the level or the depth that actually defines these two or demarcates the boundary between these two zones is called the water table. Okay, so what is the groundwater actually kind of infiltrates from the top surface, okay, and it will pass through your zone of aeration and it will get saturated in the zone of saturation. Okay, so for the water to be infiltrated and pass all through the through the layers and be a part of the groundwater, you need the zones or the layers to have both porosity and permeability. So the material that is there should be porous and permeable. Okay, and there is always going to be a layer, okay, below the zone of saturation, which is going to be impermeable and non-porous maybe, okay, so that the water that has infiltrated down and reached the zone of saturation stays in the zone of saturation and doesn't trickle further. And this area we can use, okay, or we can exploit, where we say groundwater is being extracted. So this is the region where groundwater, through which the groundwater can be extracted. Okay, so two important properties of the layers that we need when or we consider for groundwater storage and also groundwater reservoir. So you have porosity, okay, porosity, and you have permeability. Okay, these two properties of the material that is there, or rocks. Okay, so we actually talk in terms of rocks. Okay, so you need porous and permeable rocks or sediments to have to contain the water. Okay, so you have porosity and permeability. So porosity, the way that we calculate is the volume of the void spaces, void as in the pore spaces that are present in the rock or the material or the grains that are there, and the total volume of the uh, material. Okay, so this is important for us to to know. We need to know whether it is a highly porous material and highly permeable material, or it is it has high porosity but low permeability. Okay, so high porosity means that it can act as a good storage. Okay, storage of water. It has good storage capacity of water, and if it has good permeability, means the pores are actually connected. Okay, the pore spaces are connected to each other and the water can flow through these pore spaces easily. Okay, if it does not if it cannot flow through that, then obviously the water is going to just stay over there, and it you either will not know that there is water at that level, because impermeable unit, so you will not know whether water can actually transfer from one place to another. Okay, so these are two important factors that control the storage and the transfer of water. So porosity and permeability has the primary whole control over the movement of groundwater. Okay, now there are few factors which will control the
Ma'am,
yes.
how the permeability decrease with depth? You
Okay.
see that water does not percolate much through at depth.
Hmm, hmm,
It res- it rests there.
hmm.
How?
Okay, so consider an area. So you have the layers of the rocks and the sediments. Okay, so the top part is your soil. So the pore spaces are there. Okay, and they are the interconnectedness is present over there. So the water can trickle down through that. Then you have loose sediments. Okay, so the loose sediments have voids again. The pore spaces are present over here, and they are interconnected. Okay, so the water can move between the grains and still, pass through. Okay, then
Yes,
you
ma'am.
have suppose a sedimentary rock. Okay, so now the sedimentary rock sometimes has low porosity also, high porosity also. Okay, so suppose this is a sandstone. Okay, SST means sandstone. Okay, so the sandstone can be of sandstone, the grains. Okay, so the mineral grains that are present in the sandstone, they can have kind of impermeable cementation between them. Okay, so there are pore spaces in the sandstone, but those pore spaces are filled with a precipitate of a different composition. Okay, so that means there are pores, but they are not they cannot be connected. Okay, there is no connectedness between the pores because there is a material present over there. So then what happens that this becomes an impermeable kind of a layer. Okay, so there is cemented material between the grains, and the water now cannot trickle below this. Okay, so this is one kind of a way. Now the water is only going to stay in this layer. Okay, over here it
Yes.
cannot go through, it cannot pass through easily. Okay, now in place of sandstone, suppose we have an igneous rock. Okay,
Yes, ma'am.
an igneous rock is a crystalline rock. Now in the crystalline rocks you have very big mineral grains. They are kind of melted, actually molded together. Okay, there is no open space between the mineral grains over there. Okay, so that becomes a totally impermeable layer. So again the water is going to stay in this layer only.
Yes, ma'am.
Yeah,
Yes.
so there are few rocks which can, as I said, mostly unconsolidated sediments like sand, silt, or gravel. Okay, these are kind of those sediments, and if they don't have any finer material between them in the pores, then they can hold rock as well as transfer water from between the pores. So it has both high porosity and high permeability. But if you consider like well cemented sandstone or shale as a layer, now shale has, it has porosity, but it is impermeable. The mineral grains are very small and they are so fine in finer in size that the pore spaces are very small. So if they are very
Yes,
very
ma'am.
small, there is no interconnectedness. The interconnectedness, and so it becomes an impermeable rock layer.
Yes, ma'am.
Yes. Okay. So this is how the impermeable rock, if it is present, the water cannot pass through that area or pass
Ma'am,
through that layer.
water below water table is in liquid or some other states?
It is in liquid state only. See, like below water table, you can see that if we dig a well, okay, over here there is water only. So when you pump it, it can only pump the liquid part, and because this is both high porosity and there is high permeability in this zone of saturation, so the water you actually flows from this area to this area to the place where the well is extracting the water. It is in liquid form in the below the water table.
Yes, ma'am.
Yes, usually water table at some places you can find it, within 1 kilometer, where your water table is pretty shallow. Okay, so you can reach the water in the kind of that in the liquid form and easily extractable. So some
Yes,
places
ma'am.
it is 500 meters, some places it is 300 meters. So
Water
any,
table entire water table entire globe is not sharp. It may be elevated, it may be depth.
yes, yes. Like arid regions have groundwater at very deeper levels.
Yes,
We
ma'am.
will like if you like if there are maps somewhere, where groundwater levels are mapped in India itself, you will find Rajasthan actually has a deeper deeper water table.
What are them?
Yeah, and compared to when you take into consideration the Indo-Gangetic area or the West Bengal or coastal areas. Okay, so over there your water table will be shallower.
Yes, ma'am.
Yeah.
Thank you, ma'am.
Yes. So as I was saying, there are few factors which actually affect the rate of infiltration. Infiltration is like how the water is actually entering or passing through the ground layers. Okay, so you have topography, you have soil and rock type. So topography, obviously, your low-lying areas have a higher higher chances of water infiltrating at low-lying areas, because the water can stand at that area for a longer time. Okay, and in highly elevated areas, unless and until there is kind of a valley or kind of like kind of depression present, it's difficult, because most of the water will just run, it will actually occur as a surface runoff along the slopes. Then your soil and rock types, as we just discussed, if you have unconsolidated sediment, sand, silt at any place, okay, so it is easier for water to infiltrate. If the rock type over there is it cannot provide any kind of voids or pore spaces, it will be difficult for the water to infiltrate, okay, the ground. Then amount of intensity of precipitation, as we discussed, the rate of infiltration in the windward side of a mountain range is obviously going to be more than the rate of any kind of infiltration in the leeward side, that can be the rain shadow region. So if the rate of infiltration is very low at that area, you know that the water is not going to you will not find the groundwater at shallow depth levels. Okay, and obviously vegetation is going to have an effect, and again land use will have an effect on that. Okay, so this is important. Now you have two areas, that is, one is your recharge area and discharge area. Recharge area is where the surface water is actually infiltrating and recharging the groundwater reservoir. Okay, the groundwater reserves is actually increasing in amount. Okay, and discharge areas where the groundwater is actually helping in recharging of a different reserve. Okay, so to understand that, you can see over here that when we the stream, okay, any stream, okay, if it is meeting the water table, this is where your groundwater is getting discharged. Okay, if the water table is lower than the than where the stream is actually meeting the ground surface, water can trickle from the stream, okay, through the layers that are present there, and can recharge groundwater also. Okay, so stream can act as both a recharge area and discharge area. Over here, the these
Please
curve.
explain it once again.
Yes, okay. So actually this I can explain. See over here. So what is happening is, the water table over here is actually, you know, it is rising over here. Okay, you can see this is the water level over here, it is curving upwards. So the stream is actually recharging the groundwater over here. Okay, over here the water table is supposed to be like this. Now over here, now the stream is actually cutting or intersecting the water table over here. So the groundwater is actually giving its water to the stream for it to flow. Okay, can you understand the difference? Over here the water table would have been like
Yes,
this. Okay,
yes, ma'am.
now due to the stream and the sediments that it is carrying, okay, water can infiltrate through this layer and actually give its water for recharging the stream over here. Oh, sorry, this
Influent
no, this over here
streams.
it is recharging.
Yes, ma'am. Influent rivers are recharging the ground,
Ha,
and effluent rivers are discharging the
discharging
water.
the groundwater. Okay, so this is the kind of way how a stream can act as both, as a recharge and a discharge for the groundwater. Okay, so over here you can see, okay, these are different kind of layers. Okay, so you have water aquifers. Aquifers are those layers which can store as well as transmit water, okay, groundwater at faster rates. Okay, so aquifer is the suitable layer which holds the water and where actually the groundwater is usually found, under the earth's surface. Okay, so over here you can see there is unconfined aquifer. Unconfined aquifer is, it is not bounded by any layer which is actually impermeable in nature. Okay, so and confined aquifer is the aquifer which is actually bound by two impermeable layers. And then you lastly you again have a confined aquifer over here. Suppose this like an example area. Okay, so you can see with the as the depth increases, the oldest groundwater that is probably present in that area is actually at much deeper level. Okay, compared to the water that is actually either getting recharged by the stream or which is discharging into a stream. So pumped well, the wells that we dig actually cannot reach this depth. It is very difficult because our technology hasn't evolved that much. So a very old kind of groundwater is present at much deeper levels. So the type of aquifers that I said, aquifer in itself can be confined or unconfined. Okay, and then you have aquitard. Aquitard has very low permeability. Okay, and it usually occurs between one aquifer and aquiclude. Aquiclude is impermeable. Okay, but it can store water because it has good porosity. Okay, aquitard doesn't even have, it is partly permeable and it has water storage capacity. Okay, and aquifuge is are those impermeable layers that we were talking about. Okay, so aquifuge will have no permeability at all and it cannot even store water, so it has no porosity, no permeability. Okay, mostly your compact crystalline rocks like granite and basalt actually form aquifuges. Okay, and the best examples of aquifers are sand, gravel, any unconsolidated sediments without any cementation material between the pore spaces. Okay, so sandy clay actually is gives the impermeable nature to anything. So if there is a lot of clay present, the permeability will start decreasing. Okay, so your you can see in this example. Okay, so you have this confined aquifer that is actually sandwiched between your aquiclude which can store water. Okay, but it is very low in permeability. Okay, and aquifuge, there is no porosity, no permeability. Okay, so this is one example, and then you have artesian wells. Artesian wells are those wells which naturally intersect your water table. Okay, and the water, due to the pressure difference between the well and the water table, the water automatically starts moving upwards through the well. Okay, so you don't need an artificial pumping for that. Okay, so we already dealt with how the stream can infiltrate the ground to recharge the groundwater and
Ma'am,
yes,
ma'am, what is potentiometric surfaces? We have seen there
potentiometric surface.
last
Yes.
yes, potentiometric surfaces in confined aquifer.
Okay, so potentiometric surface, I think it is the level where the pressure differences actually are seen. See over here, your this is where your water table is. Okay,
Yes,
and then if you dig a well over here, you can see that the level is decreasing. Okay, for all.
Yes,
Now over
ma'am.
here it suddenly drops below the potentiometric surface. Okay, over here the water table is kind of in line with the wells being dug, but over here the water table is much below, like the water table and the level of the water that we can see over here, both are matching. So there is a decrease in the levels of the water that you can find in a well. So I think that is the reason, that is what the potentiometric surface is. But I think it's better if I give you a proper explanation for this. So I will, give you the explanation in the discussion forum. Okay, so I will just note it down. So I will look into it once to give you a proper definition of it. Okay,
Yes, ma'am.
potentiometric surface. With respect to this diagram, I will actually give you an explanation. Okay, then yeah, as you can see that in this diagram, in this map, you can see the different kind of aquifers that are present. Okay, so obviously this is not giving you the depth per se to the different, the depth of the ground water level, but you can see that there are different kinds of aquifers that are present. Okay, so very low, crystalline aquifers. Crystalline rock can become aquifers if they are fractured. They are very highly fractured rocks. Okay, so the water can trickle down through the fractures and actually get stored and can be extracted from there. Okay, so otherwise most of the the Ganges basin is mostly sediments, okay, alluvium, and then you have unconsolidated kind of, wherever you have unconsolidated rocks you can find some aquifers over there. Okay, and this is the picture on the right is actually from, I think, the Times of India newspaper. So it is giving us the picture of how the groundwater situation has changed, like from 2017 to 2020. So we have a lot of safe units, or the the where safe groundwater, or these groundwater are not under any danger of getting depleted across the country. But the areas which are very highly impacted are obviously in Rajasthan. It is overexploited, and we consider it exploited is because there is very low surface water reserves also over there. There are very few surface water bodies that are present in Rajasthan, so they are very much dependent on the groundwater. Okay, and similarly you can see some parts of Maharashtra is also there, where it is in semi-critical and critical stages. So rain shadow region is found in the Vidarbha region of the Maharashtra. So over there also, for any agricultural use or daily household use, they are very much dependent on the groundwater. So understanding the situation of groundwaters is very important for us. Okay, so that is why the changes in groundwater levels and the effects it has in also the geomorphic processes. Groundwater plays a role in geomorphic processes, so that is important for us to gauge and get an idea about how we can prevent the over exploitation of groundwater, and how it how we can try and reduce the intensity of the processes that are actually carried out by this groundwater in general. I think it's 8 now, so I will have to end the session. So any quick question if you have, or we did discuss, we interacted during the class also, and we clarified a lot of aspects and concepts. So other than that, if you have any other questions, okay, so please feel free to put it on the discussion forum from this week's content or the previous week's content. So I'll try to address those, and two points that were raised today that I could not clarify, to the extent that I would like. I will give answers to that in the discussion forum, hopefully by tomorrow itself. And hopefully this has helped you, and you can, you could get some of the doubts cleared. And as I think you might have noticed, the NPTEL team has put up the information on the the recording of the previous lecture and also the notes. So they will update it on their own as and when the recorded lectures are given to them. So obviously you can look through them again before giving your assignment, or just clearing your doubts. And so we will meet again next Tuesday at 6 o'clock. Thank you for attending, and any other queries, any doubts that you have regarding the content, you can please put it up in the discussion forum. So thank you.
Thank you, ma'am.
Yes.